much. I'll do the quick one. This one, the student wrote and said, "Oh my goodness, I am very proud and excited about this joke I cooked up." So this is home brewed, all right? And that's okay. What do you call light that has traveled 6 trillion miles and just drank 5 cups of coffee? A buzzed light year. That's pretty good, I think. Come on, the person tried, okay? I won't say their name. Yeah, there you go. Okay. No, I think that's pretty good. And I won't read your name unless you explicitly tell me to do that. So, Meg, I won't read. Oops, anyway, so. Okay, I'll do the other one next week because it's 3:11 and we have a lot to cover today. A couple of announcements first. The first homework is due next Friday, not today, okay? And you can find it in the course reader. Some people have had trouble finding it, but there's a thing called the table of contents, which is extremely useful. I spent hours typing it up. It's on page 3. There you will see the page number for the homework assignments, okay, and what questions in the book I want you to do. All right, there are these boxes outside of room 11 Campbell Hall, and they're labeled with your section number and GSI name and all that kind of stuff. So be sure you put your homework in the correct box because we're not going to sort through them. And don't get too eager about turning in homework. Don't turn it in late, but never turn it in before the Monday of the week that it's due, because it could get confused with the previous week's homework, okay? Now this week, next week, there is no Monday. There is, but it's Labor Day holiday, so have a good time. So you can start turning it in starting from Tuesday if you're an early bird, but no earlier than Monday. And certainly no later than 5:15 on Friday, okay? You got to put your name, ID number, all those kinds of things, all right? You get 2 points off if you don't have these 5 items, 2 points each. So I know that sounds high school and everything, but we have so many of these things to sift through that if they get lost or misplaced and you don't have your GSI name and section number and stuff like that, it becomes hard to filter through all this stuff. Okay, a couple other things. Because the meteor shower tonight is so obscure, I even got the name wrong on Wednesday. I knew what it was, but I called it the Aquarid for Aquarius. It's actually the Aurigid for Auriga meteor shower. So it's really a quite obscure meteor shower, but some years it's supposed to be really good, and this is one of those years. And I just got an updated prediction that someone in really dark skies, which we won't have because we're in Berkeley and the gibbous moon will be up, but someone in really dark skies with a really clear sky everywhere and everything might see 200 of these things per hour, but it's only going to last like 25 minutes. It's a very narrow stream of cometary debris through which we're passing. So under ideal conditions, you might see 100 of these things tonight. So I'm guessing 10 to 40, maybe. But you never know. Maybe under ideal conditions there would be 1,000. Or maybe there will be 10. We just don't know. But I would say give it a try if you're up tonight. 4:33 a.m. is the predicted maximum with a narrow window around that, plus or minus 13 minutes or so. So I'm going to view from around 4 to 5 a.m., maybe 3:45 to maybe 5:15 on the safe side. And I'll come out to Memorial Glade. But you're welcome to view anywhere you want or not to view it at all. But if you do view it, you might as well write it up. Just a brief paragraph or two as part of lab number 7, and you'll get 3 points, okay? All right, a few general announcements. The star parties, with the exception of Tuesday, were a smashing success, and we figured out what's wrong with the telescope, and we think we know how to fix it. So we'll have more of these things next Tuesday. So I won't be able to announce it on Monday, but I'll send you email. Tuesday, Wednesday, and Thursday from 8:30 to 9:30. We're doing it earlier now because sunset is earlier and earlier these days. We're coming into fall and winter pretty soon, so we might as well start earlier. And you can see Jupiter, the CalStar, and a bunch of other things. And then no classes next Monday, no discussion sections. You're encouraged but not required to attend any other discussion section Tuesday through Friday. You're not required to do so, but if you wish, you're welcome to go to some other discussion section in case you feel you'll miss out on something important. Okay, so go Bears tomorrow. All right. I wanted to just mention a few things that I hadn't quite finished up on last time. and also answer a few of the popular questions that many of you had, good questions, after class. We were talking about seeing into the past, how light travels 1 light year in 1 year, 6 trillion miles. And from the moon, it's 1.3 seconds, okay? Well, light travels about a foot per billionth of a second, a foot per nanometer, all right, something like that. So where's Nicholas? Is Nicholas here today? Yeah, there's Nicholas. Nicholas had GSI. He's about, 30 feet away from me, so it took light from him to me to reach me 30 billionths of a second. So I'm seeing him as he was 30 billionths of a second ago. He might not even exist anymore. Oh, he does. Good for me. I have a head GSI, and even better for him, he's still on this good earth, okay? So you can impress your friends and parents this weekend by telling them light travels a foot per billionth of a second. So that's kind of fun. So from the moon, it takes 1.3 seconds for the light to reach us. And I had a good question after class. The question was, do radio waves travel at the speed of light? Well, that will be the subject of today's lecture, but the basic answer is yes. Radio waves travel at the speed of light. They're one form of electromagnetic radiation. So when Mission Control sent a radio signal to the astronauts, it took 1.3 seconds, and their radio signal reply came back 1.3 seconds after receiving, the signal and answering the question, for a total round trip of around 3 seconds. And then the other question I got was, well, listen, since there's no atmosphere on the moon, why is the flag horizontal and appears to be waving, like in the wind, right? Indeed, there's a society of people in the U.S. and maybe worldwide who claim that the NASA lunar landings were a big hoax and that it never happened. And this is one of the pieces of evidence to which they point. That, how could the flag be doing this? Well, look, folks, the flag was set up to be horizontal. It's not a piece of cloth. It was some piece of plastic or something else, and it was set up in a Ripley kind of way. You've got one still shot here. You don't have a movie of the flag, right? The implication is that it's rippling around, but no, it's not rippling around. It's just a stiff, bent flag that they stuck up there to make it look like it's rippling around. All right? Okay, this is not a piece of evidence against the lunar landings. Yeah, anyway. Okay, the other thing I mentioned was how galaxies are all moving away from each other, but some of you have heard that the nearest big galaxy, the Andromeda Galaxy, only 2.4 million light years away, is actually moving toward the Milky Way. It's actually not moving away from us, it's moving toward us. So how is that possible? Well, the Andromeda Galaxy is part of a cluster. We are part of a cluster. Our Milky Way is part of a cluster. And in this cluster of a few dozen galaxies, the galaxies are gravitationally bound together and might be moving toward each other or away from each other. The expansion of the universe that I will talk about at length later on is really an expansion of space between clusters of galaxies, or even more correctly, between even larger structure called superclusters. But within a cluster, galaxies can and do often move toward each other. And indeed, our galaxy will merge, we think, with the Andromeda Galaxy in about 6, 7, 8 billion light years, and we will merge to form one giant supergalaxy of a different shape, actually, an elliptical galaxy rather than a spiral. Then some of you asked, well, what all this about the expanding universe, what's it expanding into, and how can all the galaxies be moving away from us? Are we special? Rest assured, this will be a huge topic of conversation later in the semester when we get to cosmology. But just to whet your appetite a little bit, in a uniformly expanding universe like this one, where you have galaxies that are ping pong balls being stretched apart by this rubber hose, you can see that if we live on this yellow one here, all the galaxies are moving away from ours, the yellow one. But similarly, if we were on any other galaxy, you see that all the other galaxies are moving away from any other galaxy as well. So there is no center. All the galaxies are moving away from all the other galaxies, modulo this statement that I made about clusters. What? Hi there. That was kind of stupid, huh? Anyway, I could say it to myself, hi there. So, thank you. I will have some demos later on, Alberto, so this is really good that it's working, because I have a whole bunch of contraptions I'm going to show you today. So we'll do that a little bit. It'll be obvious. Anyway, I like stretching rubber bands. Gives me some muscle power, and so we'll discuss it all later on more. And if you really like to think about things this weekend ahead of time, think of our universe being like a two-dimensional balloon like this. So I blow it up. Oops. This balloon must have been near some hot spot or something because it's all deformed. But anyway, blow it apart and some more and more, and not too much, otherwise we'll get a little bang. But anyway, all the stickers move away from all the other stickers, and none of them can say that it's at the unique center. So we'll talk about that all a lot more later. Can I table that question? Because we're going to spend a month on this. And come to my office hours. Definitely. Not enough people are coming to my office hours, and we'll discuss it before the time comes in lecture. But I now want to move on to the lecture material so as not to fall behind. But I encourage and am pleased by the amount of interest people have shown in questions beyond what I'm actually covering in whatever today's lecture in class. Okay, so the bottom line of last Wednesday was that, the finite speed of light gives us sort of a fossil record of the history of the universe. And that's a marvelous aspect of the speed of light. If it were infinite, we would see the whole universe as it is right now, and that would be more boring, than seeing different parts at different stages of its history. Okay? All right, now, to expand on all this, because the distances were huge and everything, let me talk about some scale models of the universe to try to put things into perspective. Because all these distances are so large that it's hard to get a real handle on them, right? So suppose we say that, let's take the sun, which is 109 times the diameter of the Earth. You don't have to memorize that, I'm just telling you, okay? Sun is 109 times the physical diameter of the Earth. And for kicks, for fun, as an intellectual exercise, let us suppose the sun were the size of a period at the end of a sentence in a typical textbook. And that's about 0.5 millimeter in size. 0.5 millimeter is really small, okay? Suppose you scale the sun down to a point on your sheet of paper. And you scale everything else in a proportional way. How far away would some common objects be? Well, the nearest star, which physically is 4.2 light years away, on this scale would be 14 kilometers, or about 8 or 9, depending on how you do the rounding, miles away. So the nearest star on a scale where the sun, which is 109 times the Earth, mind you, where the sun is the size of a period, the nearest star is 9 miles away. Okay? It's a pretty empty universe. Here's the nearest star, Alpha Centauri. Actually, its companion star, which you can't see there, is 9 miles away. All right, and the other stars are farther away still. And that's on a scale where the sun is really small. How about the Milky Way galaxy? Well, that's 100,000 light years across in real life. So scaling it down in a proportional way, how big is the Milky Way galaxy? It's about 320,000 kilometers across. That's nearly the physical distance of the moon. So our galaxy is nearly out to our moon in diameter on a scale where the sun is a period. Whoa, yeah, good, whoa. I mean, you got to go and say, whoa. We're kicking Tennessee's butt tomorrow. You say, whoa, not because we're kicking their butt, which we will, but because the Milky Way galaxy is almost out to the distance of the moon on a scale where the sun is a period, okay? That's why you should be saying, whoa. So there's a galaxy that's kind of like our Milky Way galaxy. We can't see our Milky Way galaxy from the outside because we live deep inside it. All right. So that's kind of cool. Now let's go the other direction. Instead of scaling big things down, let's scale small things up. This is actually quite instructive as well. Suppose an atom, and you're about 20 billion atoms high, roughly speaking. If you just stack them all up, you're about 20 billion atoms high. Suppose one of them, they're really small, but suppose one of them were the size of an apple. It's a lot smaller than that, okay? But suppose it were the diameter of an apple, about 8 centimeters. This is a bit of a small apple. Then a human, 20 billion of these things all stacked up, would be 1.6 million kilometers long. More than 4 times. Yeah, about four times the distance of the moon. Whoa, there you go. Humor me. Okay, whoa, right? So if each of your atoms were an apple in height, all stacked up, you would be as tall as 4 times the distance to the moon. So an atom is really small. But here's the real punchline. The nucleus of an atom on this scale, the very central part, like the proton in the hydrogen, even on this highly magnified scale, where you're 4 times the distance to the moon, an atomic nucleus would be 0.0016 millimeters. That is 1.6 millionths of a meter, microns, yes, in diameter. So the nucleus of the atom, which is the size of an apple, is way smaller than a millimeter. So the nucleus is really small. What does that imply about atoms? A lot of empty space, that's right. Here is a picture, a sort of representation of an atom, and we've greatly exaggerated the size of the nucleus relative to the electron cloud. It's mostly empty. By the way, this reminds me of a joke. A neutron walks into a bar and orders a drink and asks, how much? And the bartender says, for you, no charge. Right? Get it? Neutron, no charge. Okay. Well, anyway, a hydrogen atom doesn't have any neutrons. At least a normal hydrogen atom doesn't. But here, the distances are exaggerated. But this is like 5 times 10 to the minus 11 meters, and the radius of a proton is only like 5 times 10 to the minus minus 15 meters. But a hydrogen atom is sort of emptier than most. If you take more representative atoms, then you find that, in fact, most atoms, hydrogen is emptier than this, but most atoms are 99.9999999% empty. And you can count them. There are 12 nines there. So the nucleus of an atom takes up one tiny, 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 tiny fraction of a percent of the entire thing, defined by the size of the electron cloud. And the reason atoms are so big and empty is dictated basically by 2 very fundamental things in quantum theory, which I will discuss in some of the evening, what I call bull sessions, which I will organize later in the semester once you know more astronomy and stuff, where we can just discuss anything you want. And they're optional, but you can throw any questions you want at me. But one of the things we discuss one evening is quantum mechanics. And there's a thing called the Heisenberg uncertainty principle, which basically tells the atom that it can't be any smaller than this. And then if you start adding additional electrons, suppose you don't just have hydrogen and helium, you have heavier elements with more electrons, a thing called the Pauli exclusion principle keeps those electrons from all piling up in the inner orbital. They have to go to other orbitals and stuff. So it's these 2 principles that make atoms relatively big in terms of their electron cloud compared to the size of the nucleus. So that's just kind of an interesting, funny little thing. Okay? All right, so on to the main topic of today's lecture, and that's light. Okay, so here's a bunch of stars, and astronomers are at a disadvantage compared to other scientists. A biologist can take an apple and cut it open and study the insides and immerse it into acid and study the reactions and weigh it and find out how much it weighs, and immerse it in water and find out how much water is displaced and thus measure the volume, and they can whack rocks with a hammer and break them open and stuff. Astronomers can't do that. We can't, generally grab the things we are studying. You can't go to Ace Hardware and buy a star. You can't even buy lowly Pluto, which has been demoted, With few exceptions, the clues we get to the universe come from the light that the objects emit or reflect, in the case of moons and planets. Yeah, true, we've gone to the moon and picked up some rocks, and we also can pick up little meteorites that come landing on Earth. And there are also particles, charged particles called cosmic rays, that come from outer space, and we can collect them and learn something about objects out there. But those are the few exceptions. Most of the information astronomers gather is through the light that they receive from objects. So it behooves us to understand just what light is. Moreover, light is one of the most fascinating things in the universe and gives you a good example, a good sort of introduction to quantum theory if you wanted to study quantum theory later on. So it's just a wonderful phenomenon. So let's discuss what light is. And I think, unless you've discussed it before with other people, you'll find that the results are somewhat surprising. So what is white light, like sunlight? You take sunlight and you pass it through a glass prism, and you find that it gets spread out into a rainbow with many component colors that you can remember through the mnemonic Roy G. Biv. He's a friendly fellow that I knew when I was a kid. Not really, but you can think of him that way. And, you know, it stands for the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Now, people don't generally use indigo anymore. It's sort of an obsolete term, but the color is there. It's just not used. So you have this rainbow, okay? And you've all seen this rainbow, hopefully in high school, when passing light through a prism, but you've certainly seen it when light passes through natural prisms, that is, raindrops. You get this rainbow, okay? So white light appears to consist of these different colors, and Newton did experiments that showed that. I mean, it was known before Newton, but Newton actually recombined the dispersed light, that is, the colors of the rainbow. He passed it through other kinds of prisms that recombined the light, and he got white light back again. So he showed that it wasn't something about the glass that imprints color on the light. The light itself has intrinsically these colors, which the glass allows you to see by spreading them out. Newton did a lot of great things, and experiments with light were among those things. So white light consists of these different colors. And you could plot the brightness or the intensity of the light as a function of color. And if you do that, you plot the brightness along one axis like this, and the color along the other, and you'll get some distribution of brightnesses. For example, sunlight happens to be brighter in the yellow-green part of the spectrum, as it's called, than it is in the blue or violet parts or the red parts. So there's some distribution of brightnesses like this, and in particular, this plot is often what scientists call the spectrum of an object. You pass light from that object through a prism or an equivalent device, and you measure the brightness as a function of color, and that gives you the spectrum. And the spectrum can tell you all sorts of interesting things about objects: their chemical composition, their temperature, their pressure, and things like that. And it turns out that what we're actually doing is measuring brightness as a function of wavelength, and I'll be discussing that a lot more in a few minutes. But to give you the bottom line, visible light is simply one form of a very broad category that we call electromagnetic radiation. And the different wavelengths of these electric and magnetic fields of electromagnetic radiation are perceived by us to be different colors. So now I'll spend much of the rest of the lecture explaining what I meant by all that and telling you in a little bit more detail what I meant. So let's consider electric and magnetic fields. So here's the electric field of a stationary positive charge. I've drawn all these little arrows going radially away from it. That's because if I were to put another positive charge next to it and release it from rest, it would go zipping away from this positive charge along these radial trajectories, okay, depending on where I happen to release it. So we say that a proton, for example, is surrounded by an electric field that acts upon other charges in this manner, along these radial lines. And if you had an electron here, a negative charge, it would be attracted to the positive charge along these radial lines like this. So that's the electric field of a stationary charge. Now let's look at a related phenomenon, the magnetic field of a stationary magnet. A bar magnet looks something like this. It's got a north pole and a south pole. And you can draw associated field lines which sort of tell you in what direction the forces around the magnet act. And magnets are kind of cool because if you break them in half, you still get a north pole and a south pole. And if you break it in half again, you get another north pole and a south pole, and so on. So you never have single north and south poles, unlike the case for electric charges, where you could, in principle, have just one charge in the universe and it's not matched by a negative charge anywhere else. Magnetic fields appear to always come in pairs. And you can really visualize the field by putting a bar magnet underneath a sheet of paper like this, and then taking some iron filings and just sort of sprinkling them on the paper. And you don't have to zoom up on me. I'm just sort of, because there's a nice photo of this right there. But then you kind of jiggle around to let them get to where they want to be, you know. And those in the front row for sure can see this, you know. And you probably have done this before. And you can sort of see how these little hairs, these little iron filings, naturally align themselves along what we call lines of force, and they're illustrated right there, okay? So this is where I want to, oops, yeah. These things can be really, dang, I missed, oh well. This is the way it goes. Let me close this because it'll get all over the place. Okay, so this is where I do want to show some demos, so you don't have to have the camera on the screen. I'm kind of obsessed with magnets. What time is it? So I can tell myself how much time I have to spend on demos. Okay, 3:35. Okay, good. So I'm kind of obsessed with magnets. I love magnets. I mean, magnets are just wonderful. I mean, you can feel the force. I mean, here are these little dime store magnets, and there's something there pushing them apart, you know, and or attracting them. And you know, we're all so used to gravity, we take it for granted. But here, you play with magnets, and you can feel that there's something extra there. And here I have one. I'll put this magnet there, and this other one up here. And this is kind of fun, actually. I like doing this. If I could, I used to have 2 or 3 that go through the pen, but I lost 2 of them. But anyway, so this is kind of fun, right? You know, yeah, it's kind of floating there. Now I'm easily amused, as you can see, but yeah, you know, I'm sometimes late at night at the observatory. There's not much to do. You're gathering data, so you know. Instead of watching some porn flick or something, you play with magnets, and so. No, I'm just kidding. You know, so anyway. No, I'm just kidding. You don't. It's not that you play with magnets and watch a porn. Okay. I'm digging myself deeper and deeper into a hole. Okay, so these are really fun. You know, they're just fun to play with. And I got these a couple of weeks ago. These are really crazy things. And you throw them up and you, oops, that didn't work very well. But yeah, those are fun, aren't they? Yeah, I really get my jollies out of these things. Oops, I missed. Okay, but they're supposed to make a lot of sound. Dang, can't get it right. There we go. That was a bit better, but. There are people who can do this really well. That was not bad, but there are people who can, anyway, so they're fun. You know, like, oops. Look at that, just picked it up. So that's really cool, and, you know, you take this thing, and you set up a magnet here, and they can repel one another, and then if you do it at the right frequency, you can even make a motor. Look at that, I just invented a motor. Oops, that was done 100 years ago. But, you know, that's the spirit of invention, you know. So that's really great. And, you know, when I was in about the 1st grade, I was at a school where they kind of emphasized rote memorization and stuff. But I like to play with magnets, and I had them in a sandbox, and I dragged them around, and I found that in the sandbox, oh, it's good, actually, that I spilled some stuff. I drag it around, and then there'd all be this hair growing off of this magnet, you know. These are iron filings, but I didn't know that at the time. Iron tends to be often associated with quartz crystals and things, and so I'd pick this stuff up and I'd worry about it, and occasionally I'd find a BB someone lost in the sand. And so this was really great. You know, I was wondering, what in the world is magnetism? And the school officials thought that I was weird, okay? And they thought I was antisocial, which was not true. I remember playing Red Rover, you know, and I remember one game where there were like 30 people, and I was the last one, and, you know, only one of those people had to tag me, but I got to the other side of the field without anyone tagging me, so I was the king of not rock and roll, king of Red Rover. Maybe I'd like to be king of rock and roll, but anyway, he died some time ago, 79, 78. So, well, they thought it was weird, and they thought that I eat way too many peanut butter and jelly sandwiches and stuff. So they told my parents I should go and see a child psychologist or something like that, which in and of itself is not a bad thing. You know, I'm all for therapy, but they thought I was weird. And instead of nurturing a clear, genuine interest about nature, they thought that I should, you know, be memorizing a bunch of facts. So my parents didn't like that school, and they took me out, and they put me in some other school. And they said, ooh, you like magnets. Well, if you go to the library, you can find a book that will tell you how to control this phenomenon. I go, oh, man, is that great or what? So I went there, and I checked out the book, and sure enough, you can wrap a wire around a nail, and that nail normally then, you know, wouldn't pick up a paper clip or a screw. But if you attach the other lead, shoot, this one came off. Where'd it come from? Oh, can't see very well. This little gripper isn't gripping well. There we go. And then I take this one and I attach it. Why can I not see? There we go. And now watch. It'll, yeah, look at that. It picks up that paper clip, you know, or actually that's a screw. But a paper clip would work also. See, here's a paper clip. picks up the paperclip too. And then if you unhook it, you know, they fall off. So I suddenly was master of the universe, or at least of magnetism. And it was important, you know, to me to understand what it is. But already you can see that there's a deep connection between electricity, a current going through a wire, and magnetism. Because a current going through a wire creates a magnetic field. In fact, there's a compass here, and when I hook this up, the needle of the compass goes crazy if I put the nail next to it. So a current going through a wire produces a magnetic field. There's a deep connection between the two. And similarly, it turns out that if you have a changing magnetic field somewhere, you can induce a current. I'm sorry, if you have a current makes a magnetic field, but you can also, there's a deeper connection as well. The magnetic field oscillating in a particular way can induce a current in a wire. So there's this deep connection. And James Clerk Maxwell studied the various equations that his predecessors had come up with, describing electricity on the one hand and magnetism on the other hand. And he did two important things. First, he modified one of the equations that his predecessors had come up with. He added an important term to that equation. And then looking at the equations, he started playing with them mathematically. And he realized that after playing in a certain way with the equations, out popped a quantity, a combination of various constants, that described an oscillating, that is getting bigger and stronger and weaker, field of electricity, and also an oscillating magnetic field. And these two oscillating fields generate one another. So the oscillating electric field getting stronger and weaker, that generates a magnetic field, which in turn becomes stronger and weaker and stronger and weaker. And that regenerates an electric field that gets stronger and weaker. And the combination propagates through space at a certain speed. What speed do you think that was? C, the speed of light. So Maxwell, one of the greatest physicists of all time, showed that light is a set of oscillating, self-generating, propagating electric and magnetic fields. And he was able to derive its speed from these four equations that describe the properties of magnets and of currents and of electric fields all independently. So he showed that these equations, first, are related to one another, and second, when put together in the right kind of a way, describe or predict the existence of light. So I have this t-shirt that I'm wearing here from Purely Academic. Several people have already asked me where I get my t-shirts from a number of locations. Purely Academic is one. There's another place called Velocities. But if you Google physics, astronomy t-shirts, you'll find vendors of these things. Here it is a little bit closer. And God said, and then these four equations, and then there was light. Okay? So light is these four equations working together in the most mathematically beautiful way. And this is what's called the integral form of the equations. I have another t-shirt which has them in differential form. And don't worry about these equations. You don't need to know them. Just know that they exist. The integral equations are more useful for solving some kinds of problems. The differential form is more useful for other kinds of problems. But they all describe light, and they show that electricity and magnetism are like two sides of the same coin. And there was this unification of two forces, electric forces and magnetic forces, that Maxwell came up with. And this is a repeating theme in physics where we try to unify many seemingly disparate phenomena. You could say desperate, but disparate phenomena under one umbrella. You explain lots of phenomena with the same fundamental idea. That's beautiful. In the end, we'd like to have all of physics fit on one t-shirt, one equation. I'll have more to say that later when we talk about the earliest history of the universe and the Big Bang and stuff. But anyway, that was one of the first examples of this unification. So what Maxwell showed, is that there are these electromagnetic waves which are electric and magnetic fields getting stronger, 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 weaker, 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 passing through zero, then getting stronger in this direction, weaker, and so on. And this change in electric field generates a magnetic field which itself changes and regenerates the electric field. And both right here, for example, are zero. They have a value of zero. But that's okay. You might think there's nothing there. Yes, instantaneously there's zero electric and magnetic field there. But remarkably enough, since that zero is changing, the fields are going from being positive to negative, they keep on reinforcing one another and they allow the wave to continue propagating at the speed of light forever, unimpeded. Of course, if it hits the screen or something, then it bounces off or gets absorbed or whatever. But light through a vacuum goes forever, unimpeded, because it is the set of perpendicular electric and magnetic fields which oscillate in a direction perpendicular to the direction of motion, and that motion, through a vacuum at least, is the known measured speed of light. So light is an electromagnetic wave. And visible light is just one example of this much more general phenomenon, electromagnetic radiation. What's the wavelength? I mentioned that earlier. Well, let's take either the electric or magnetic field. It oscillates like a wave. It gets stronger and weaker and so on. The distance between two successive wave crests is the wavelength, usually denoted by the Greek lowercase lambda. You could take two successive troughs as well. That would be one wavelength. Or you could take two successive corresponding parts of the waves. That would be one wavelength right there. Okay, so that's the wavelength, the distance between two successive crests. Okay, there's a related quantity, the frequency nu, usually given by this little Greek lowercase nu, but in many textbooks is given as f, script f, because nu is easily confused with v, the speed. Don't do that, okay? Anyway, physicists use nu, so I'll use nu, but it's the frequency. It's the number of times a second that crests pass a given point. So pick a point P, call it Q, right there, and count how many times per second crests pass by you. If 10 crests pass by in 1 second, we say the frequency is 10 waves per second. Sometimes people use the word wave implicitly, so then it's just 10 per second, or 10 hertz, kind of like a Hertz donut, but you know, it's Hertz, like the Hertz rental car company, but it's 10 per second, okay? And clearly, if 10 waves are going by per second, what's the period of one wave? It's just 1/10 of a second, right? If there are 10 of them per second, each one takes up only 1/10. If there are 100 of them per second, how much does each one take up? 1/100th of a second. So clearly the period of a wave is simply the reciprocal, the inverse of its frequency. So nu to the -1, that's just a fancy way of saying 1 over nu, that is the period p. And then, taking these two quantities together, you come up with an interesting third quantity, and that is that if you multiply the length per wave, well, that's the wavelength, by the number of waves that go by per second, that's the frequency, then the waves cancel out here and you get length per second. But what's length per second? It's speed. It's like miles per hour. Many of you will take road trips this weekend. You'll go some number of miles per hour. That's a speed. A length per second, or length per unit of time, is a speed. So the speed of a wave is its wavelength times its frequency. And this is a very generic result. It's true for water waves, for sound waves, for light waves, for slinky waves. It's true for waves in general. And in the case of light, that speed v is equal to c, the speed of light. Okay? So it's an electromagnetic wave. Any questions so far? Expanding on, yes, what's your, Brett? No. Brett, I got it right. How do you like that? Okay, Brett, yeah. And you're even sitting in a different spot this time. Okay, anyway, go ahead. Brett asks, since C is always the same, if we know one of those quantities, wavelength or frequency, we can figure out the other. Absolutely. In a vacuum. Now, in glass or air or water, the speed of light slows down, it turns out. So once you know its retarded speed, you could figure out the wavelength or the frequency depending on what the other variable is. But yes, knowing one of the two and the speed of light, you can figure out the third. That's right. Okay? So let's repeat this again then and ask ourselves, okay, what about visible light, the light with which we're most familiar? Well, that's light of a particular wavelength. It's often measured in these things called angstrom units. 1 angstrom is 1/10,000,000th of a meter. Okay? 10 to the minus 10 meters, or in more traditional units, a tenth of a nanometer. Or these are the preferred units. I guess the traditional ones are angstroms, but physicists now tend to prefer using, multiples of a meter that have some thing in front of them instead of angstroms. But anyway, I don't really care what you call them, but the red, yellow, green, and blue ones are roughly, in the case of green, let's say 5,000 of these angstroms of 5,000 times a 10,000,000,000th of a meter long. So visible light is about yay big, and I exaggerate a lot, right? It's tiny. Green light is 5 times 10 to the minus 7 meters. It's 0.5 millionths of a meter, I guess, in length, right? So it's very small. These things are very small, but you'll see other kinds of waves that are longer and other waves that are smaller still. So different colors of light correspond to different wavelengths of this oscillating electromagnetic field, this electromagnetic radiation. So when you look at a rainbow, you can think about electric and magnetic fields oscillating around, propagating in a direction perpendicular to the two things. I actually had a little demo here. It's not a very fancy demo. One reason I use these little home-brewed demos is to show you that you don't need fancy equipment with which to illustrate things for yourself at home. You can make these things. You don't have to buy them for large amounts of money. So here's just 2 coat hanger wires where you've got this light. This is the electric field, and this is the magnetic field, and they're oscillating, kind of flipping back and forth in a sense, and they're kind of cruising along like this. Yeah, it's not very effective, but it's better than nothing, okay? So if you then say, okay, the visible ones are some quite restricted range and wavelength, are there other possible wavelengths? Sure, there's lots of them. You don't have to memorize the numbers here. You should know the 5 or 6 different main categories of electromagnetic radiation, but there's the visible light, that's the optical light, it's also called, between 4,000 and 7,000 angstroms. Now, if you go to the infrared, that's what we sometimes call heat rays. I mean, if you're near a fire, the coals are glowing kind of orange hot. You're only seeing the tip of the iceberg. Most of the heat that they're emitting is at waves that your eye is simply not sensitive to, but your skin is. You feel the heat. Those are called infrared. There's some animals, especially nocturnal ones, that see at infrared wavelengths. During wars, we have military equipment that uses infrared sensors, and they can see tanks at night because tanks glow. They're warm. We'll talk about that more next week, and they glow at infrared wavelengths. So that's these ones here. If you have really long ones, a millimeter in length or longer, then you call them radio waves, okay? Or you can have short ones, ultraviolet, or even shorter, X-rays, or even shorter still, gamma rays. And gamma rays have no limit to short wavelengths, just as radio waves have no limit at long wavelengths. And all these guys are generated by just having a changing electric or a changing magnetic field. So I could take this bar magnet, I could oscillate it. Its magnetic field is no longer stationary. There's a kink going along. It's changing, and the changing magnetic field generates an electric field, and that then regenerates a changing magnetic field. And so what I'm doing here is I'm emitting electromagnetic waves. They happen to be radio wavelengths because I'm oscillating this pretty slowly. The frequency corresponding to visible light is about 100 trillion per second. 100 trillion or many hundreds of trillion hertz. So I'd have to go like, some bumblebee on drugs or something, and maybe I'd get an optical photon, but I'm not going 100 trillion times a second, or 600 trillion, which is what you need for yellow or green light, So I'm not even getting close. the best I can do is create some radio waves. So if you had a radio receiver that were sensitive enough, you would hear me, making all these radio waves. But all these things can be generated in the same way. They propagate out from the magnet in all directions. They go through our bodies and stuff and so on. And so there are all these waves, and basically they're all described by the same equations. You've got all these gamma rays, X-rays, ultraviolet, infrared, radio. They might be detected using different kinds of telescopes and detectors. For example, gamma rays are detected above Earth's atmosphere because fortunately for us, Earth's atmosphere blocks gamma rays. If it didn't, we'd have a lot of cell mutations, which generally would kill us, okay? So you need, telescopes up in space to see the gamma rays, but it's the same kind of thing as visible light. Similarly, X-rays. Our atmosphere blocks X-rays, but they're fundamentally the same thing as visible light. Ultraviolet is also blocked largely by the atmosphere. Okay, so you need space telescopes. Then there's infrared and radio. Well, radio can be detected on the ground. Some of the radio waves actually pass through the Earth's atmosphere, some don't. Infrared, it helps to be in space, but you can detect some of them from the ground. So all these things are the same thing, just quantitatively different, not qualitatively different. And that's the point I'm trying to make here. These equations that Maxwell played with and the realization that they together describe visible light, well, that led to the realization that they describe a much more general, widespread class of phenomena, electromagnetic waves of all kinds, radio waves, infrared, visible, ultraviolet, X-rays, and gamma rays, okay? There's no qualitative differences between these different types of electromagnetic radiation. There may be different detection techniques and different places on Earth or in the atmosphere from which you detect them, but qualitatively they're all the same. And we are privileged to see only a tiny fraction of all that exists. We see only the ones with a wavelength between about 4,000 and 7,000 angstroms. You go back to this, and this is on what's called a logarithmic scale. Each tick mark is a factor of 10 increase in length. This is not what's called a linear scale. This would be a linear scale. A logarithmic scale is where I take one step, and then my next step is 10 times bigger, but I represent it with the same size step. And my next step is 10 times bigger than that, and I represent it with the same size step, and so on. That allows you to fit a vast range of scales, of size scales, onto a single sheet of paper. Or 2 sheets of paper. So these things extend over a broad range of wavelengths, and we see only a tiny fraction. But it's a much more general phenomenon, and astronomers are interested in other forms of electromagnetic radiation. And then the final thing I wanted to talk about today, actually I want to talk about photons, but I'll do those on Wednesday, is that, as I've mentioned before, all electromagnetic radiation in a vacuum travels with the same speed, c, and you cannot exceed that speed, c. Now, again, it slows down in glass or water or whatever, and it slows down by an amount that depends on its wavelength, and that's precisely why glass spreads white light into its different colors or wavelengths. It's because the speed of light in glass depends on the wavelength, and so the amount of bending that occurs depends on that. But through a vacuum, they all travel at the same speed, c, and that's the maximum possible speed. And interestingly, if you assume that you can't go any faster than that, and if you also assume that in a frame of reference, like an airplane that's moving with a constant speed, without any bumps, without any accelerations, if you assume that that's just as good a laboratory as one that's stationary here on Earth, and it is basically, you can't tell the difference, right, when you're on a smooth airplane flight or on a cruise or something. You eat the same way, you play ping pong the same way, right? You don't have to take your motion into account, right? So if you assume that uniform motion is just as good and can't be distinguished from a state of rest, and you assume that you can't go any faster than light, those are the two fundamental assumptions of Einstein's special theory of relativity. And the weird thing that happens then is that you get E equals mc squared and all this other stuff. You get the equivalence of energy and mass. You find that you can't exceed the speed of light because it would take an infinite amount of energy to do so. You find that if I shine this laser here in this room, I measure a speed of light of 300,000 kilometers per second. But if I move my hand toward this thing at half the speed of light, I still measure a speed of 300,000 kilometers per second because the speed of light turns out to be independent of your frame of reference. You find all these weird conclusions. But if you then ask, what are the experimental consequences of those conclusions? They end up being reality. They end up being what we know to be true to the degree that we've made experiments. And speeds and things don't add up and behave in the Newtonian way. Things are actually really weird, but counterintuitive to us simply because we don't spend much of our time zipping around at high speeds. But in one of these bull sessions, I'll describe relativity and its consequences much, much more. But it's based fundamentally on two assumptions. You can't tell if you're in uniform motion, and the speed of light is a maximum constant above which you cannot go. Okay, have a great weekend and go Bears. Thank you.